Keeping an eye on the numbers, and we've still got a few people rolling in, but let's get started anyhow. I like to be punctual. For day 2, so who are we going to first today? Annie, is it you?
Yeah.
All right, let's just hand over to Annie. Same as yesterday, utilize the chat function. Yeah, type your questions and we'll keep an eye on it. All right, I'll hand over to Annie. Thanks, Annie.
Okay. You should all be able to see that screen now. Just get rid of this. Yeah, so feel free to use the chat to ask any questions you want or make any comments. I'm very happy for this to be more of a discussion than a lecture. And I'll just pop out the chat now so I can actually see it. Okay. So just to kind of pick up where we left off yesterday, this is a picture of the dyes in 2 different fluids that had been disturbed and added a little bit of turbulence to them. And on the left is non-rotating fluid, and on the right was a rotating fluid. And you can see that they have this really streaky pattern of the 2 different dyes that are not mixing together very much at all. And you can see that it's sort of this 2D flow rather than the more 3-dimensional flow that you see on the left-hand side. And so we'll just pick up where we left off. And so these were the equations of motion that Marty showed us yesterday under a tangent plane approximation. So we're using X and Y instead of longitude and latitude, and Z is in the vertical. And so you see you have your time rate of change of the velocity, so your acceleration, a Coriolis force, pressure gradient force, and viscosity or friction. And then on the bottom you have hydrostatic balance, so the vertical pressure is related to the density and gravity. And so we're just going to jump right in. This sort of geophysical fluid dynamics is generally thought of as low Rossby number, high Reynolds number. So the main balance that you have here is between Coriolis and the pressure gradient. And again, in the vertical, you have a hydrostatic balance. And so in the horizontal, that's what's known as geostrophic balance. And in the vertical is hydrostatic. You can write it in a vector form there on the right for those who are sort of keen on math. And if you assume a constant density, you can, sorry, I should just back up quickly. The first thing I'm going to talk about is one of the main consequences of geostrophic balance, and that is this columnar flow, 2-dimensional sort of Taylor column fluid motion that you saw in that picture that I showed in the beginning of the talk. And then I'm going to talk a little bit more about geostrophy itself, and then we'll go into thermal wind balance, which is the combination of both of these 2 balances together. Geostrophic and hydrostatic make thermal wind. We're going to just start by looking at the geostrophic balance and showing that you can, showing the mathematical foundation for why these Taylor columns exist. So if you assume a constant density, and in fact, you don't actually have to assume constant density, you can just assume a barotropic flow such that the density is a function of pressure alone, but for ease, we'll just assume a constant density. And so you can bring that term, that density term into this gradient here. And then if you take the curl of the momentum equation, you produce a vorticity equation. So taking the curl of this, these 2 terms are exactly equal to 0 due to vector identities. The curl of a gradient is, the curl of the gradient of a scalar is 0, and you can, it's written as G here, but you can think of gravity as a geopotential gradient. And so you're left with this equation here at the bottom, which can be rewritten again, using some vector identities that have to do with the curl of two vectors, I guess you could say, and the fact and continuity equation. So if you rewrite this out, there's 4 terms and 3 of them are exactly equal to 0. And so you're left with just this one term here that says that the rotation dot the gradient of the velocity is exactly equal to 0. If we assume that the rotation vector is in the vertical, then this can be simplified to there's no vertical change in the velocity. So that is Taylor-Proudman theorem in a nutshell. So that the velocity of a slow, steady, frictionless barotropic fluid does not vary at all in the direction of the rotation vector. So there's in this case, on a rotating sphere, the velocity cannot vary at all in the vertical. And so all 3 components of the velocity that is true for, so the zonal velocity, the meridional velocity, and the vertical velocity all are constant with depth. And then if you think about the ocean or the atmosphere, that the ocean surface or the bottom of the ocean or the ground at the bottom of the atmosphere or even the top of the troposphere, you can think of those as solid boundaries where there's no vertical motion. So that if they're anywhere in the water column or fluid column, there's no vertical velocity. So for example, at the bottom of the ocean, there's no velocity down or up. That's the boundary condition. Then there's no vertical motion at all. Oh, sorry. And so that is how you get these, sorry, I'm just moving the chat around. That's how you get these vertical columns in the fluid to remain vertical, and they can't be tilted or stretched. And we think of this as the rigidity or the stiffness of the fluid in the vertical direction so that the flow becomes 2-dimensional. And that's what you see in this right-hand side. And as a consequence of that in the ocean, for example, the fluid tends to flow along bathymetric contours, so along constant depth contours. So this is a picture of the velocity mapped at 700 meters depth from a bunch of float velocities. And you can see, especially along this sort of boundary of the basin, along this isobath and around here, all around here, you see that the flow wants to stay on whichever isobath it is on to begin with. And these are direct observations from the ocean. And so before we go, I'll just ask if anyone has any questions about that. Oops. How do I go back? And if not, then I will play a video. Go away. Okay, so can everyone see this?
Yep.
Okay.
Yeah.
So this is going to be a rotating tank experiment that shows these Taylor
Let's
columns.
take a quick look at the concept of the Taylor-Proudman theorem in the lab. Here we have 2 views from above and from the side of a tank that is in solid body rotation, such that the water is essentially at rest with the rotating tank. The particles behave as passive tracers at the surface of the fluid, so they move with the fluid. The dye reveals the flow through the rest of the depth. There is a small round obstacle on the bottom of the tank here with a cross. We slightly perturb the tank rotation rate so that the water begins to move relative to the tank. For the water to flow over the obstacle, continuity requires that it have a non-zero vertical component of the horizontal velocity, which contradicts the Taylor-Proudman theorem. Now, as we see here, The obstacle, even though it is relatively small and on the bottom of the tank, it has a significant influence on the flow throughout the full depth, including the surface. The traces resist flowing over the bottom feature and prefer to flow around it. But there is water above this feature, which is marked red, and you can see that it tends to remain there. That is, by way of the Taylor-Proudman theorem, bottom topography can affect the residence times of surface flows above topographic features.
So you can see very clearly there when they changed the speed of the tank, that blue dye going around that obstacle rather than over it. And so in that sense, the ocean and the atmosphere are very much steered by the bathymetric topography underneath it. Okay. I'm just seeing a question from Ewan about, can we get Taylor-Proudman without assuming geostrophy? And yeah, so Marty says the theory applies to geostrophically balanced flow. So I think the answer is no, and I agree with that. And he goes on to say, but the theory of quasi-geostrophy includes a lot of the same properties and assumes that the flow is close to, but not exactly in geostrophic balance. And in the experiment yesterday, I'm assuming the fluid wasn't in. Yeah, so for most of the world, it's not in geostrophic balance because there is an acceleration. So the velocity does have a time component to it, but in quasi-geostrophy, which we'll get into either later today or next year, you do allow for some of that acceleration, but you still have a lot of these same principles. So if you think about the video we just saw, you did see some of the red dye actually spilling down over and off of that little puck that was there, or obstacle that was there. And that's because of some other second order motions that also exist in the fluid. And Felipe asks, does it happen above seamounts close to the surface? I would say yes, it can. I don't have examples of observations of Taylor columns, but I can look for those. In general, it's more about how the flow is steered along isobaths. And so it wants to, the flow can't stretch or squeeze in the water column, or it doesn't want to. And so it tends to flow along these isobaths. Okay. Okay, so this is the same slide as before, just to remind you that these are the two main balances that we have for large scale geophysical fluid dynamics, or fluid dynamics on a rotating sphere. And you can write geostrophy in this notation if you want to do it in vector notation for those that prefer that. And again, this is the balance between the horizontal velocity and the horizontal pressure gradients. But note that the zonal pressure gradient is balanced by meridional velocity, and the meridional pressure gradient is balanced by the zonal velocity. So that's this, comes from this curl of the vector, of the velocity. And so this is a map. These are two maps of the sea surface height. So you can think of sea surface height as pressure, and you see this on the left is a model mean, and on the right is the satellite altimetry, the sea surface height observed from satellite. And you can see here the East Australian current, you have this strong change in sea surface height, and that's associated with a strong current going to the south. And this is a weather map from this morning. And you can see these high and low pressure systems, and where the isobars are squeezed closer together, you get stronger flows. So for those of you in Tasmania today, you know we're getting hit with some pretty strong southeasterlies right now, and the weather is pretty garbage outside. So sorry, I'm just looking at a question here. Yeah, so the question is about how it might differ with different latitudes, and then about baroclinic versus barotropic flows. So we will talk about baroclinic flows a bit later when we talk about thermal wind. And the different latitudes has to do with how Coriolis parameter goes from 0 at the equator to its maximum at the pole. And so that does affect the flow, but for scales of, for length scales and time scales that permit low Rossby numbers, you generally get this flow along isobars or along sea surface height contours. Okay. So again, geostrophy is the main balance, and you do see this along pressure contour flow of the horizontal velocity. And so we can call that a geostrophic velocity or geostrophic current. And you can take the curl and then find that it is directly related to the horizontal pressure gradients tweaked by rho and F. And again, it's along contours of constant pressure. And so this is for the northern hemisphere, where F is the Coriolis parameter is positive. You have geostrophic current with the high pressure to your right. In the southern hemisphere, it's opposite, with the geostrophic current with the high pressure to the left. And if you want to sort of think about why yeah, so Yanyap just said it in general for large scale flows, instead of isobars, it's F over H, which is geostrophic contours for planetary flows, which is correct. As the flow wants to conserve something called potential vorticity, which Navid will talk about a bit later on today as well. And just as a, if you want to sort of visualize why F would be positive in the northern hemisphere and negative in the southern hemisphere, you can actually, if you have a pen handy, you can just spin it in one direction and look down, and you can see it goes around, say, clockwise if you're looking down on it. And then if you keep spinning it and look this way, you'll see that now it's going anti-clockwise. So even though the Earth is spinning in the same direction, you have these different realizations of the torque. Okay, so now we're gonna move on and talk briefly about baroclinic flows, and going to get into thermal wind balance. So what if we now say, instead of a constant density, that we have a density that varies in both space and perhaps time? Does anyone have any thoughts about what might happen or how the flow might be different. So before, with a constant density or barotropic flow, we had no change in the vertical of the velocity. So the velocity was constant with depth. And so in a baroclinic flow, just with a show of hands maybe, or just think to yourself whether you think that would be the same in a baroclinic flow and why that might or might not be true. So I can't actually really see anyone, but all the videos are off, that's okay. So imagine we have a metal cylinder we have a tank with fresh water on the outside and salty water on inside of a metal cylinder. So this salty water is now more dense than fresh water based on the equation of state. So if we pull this cylinder up and let that dyed salty water, that denser water, re-equilibrate in a non-rotating tank, what do you think will happen? What do you think the picture will look like? You can either write it in the comments or just think it to yourself. And yeah, so we have a few comments coming in saying the salty water goes to the bottom or the fresh water will sit on top, and that is exactly right. I don't have a picture of what this would happen, but you would have a 2-layer system with the dense water on the bottom and the light water on top, with that interface between the two density layers being exactly horizontal. But now if we add rotation to the tank and we have it in solid body rotation before we pull that metal cylinder up, can people guess what might happen then? And again, just write it in the chat. Okay, so we have some good answers here. One says it stays in the middle a bit. Another says there's a sloped barrier between the dyed and the fresh. And maybe I would challenge you to think about which way the barrier would be sloped. A center of vortex of salty water. These are all good suggestions. And yeah, what you see is that the system geostrophically adjusts into this frontal system, where instead of having a flat barrier or interface between the two density layers, you have this sloping barrier where the denser water is sloped downward, so it's thicker at the bottom than it is at the top. And this is an example of what that would look like in the tank. If you actually did this experiment here and ran it, it would look like this, and you'd have this sloped, dense fluid in the center. Oops. And yep, we'll get back to that. And so here's an example from the ocean. So there's a ship that runs from Long Island to Bermuda fairly often, and it goes right across the Gulf Stream. So you can see in this sea surface temperature map, this warm current, which is analogous to the East Australian current, but this is off the eastern coast of the United States. So it's the western boundary current of the North Atlantic gyre. And when you look in temperature, you can think of temperature as density. You do see these sloping isotherms, and associated with that, you see this strong velocity. So that's where some people who are mentioning a vortex, it's not quite a vortex of salty water as it goes throughout the water column, but you do see this intensification of the velocity with height in the water column. So this is this was just one section, one transect across. And if you look at an average over a couple of years, you see this temperature gradient in the horizontal, and that's associated with this strong jet. So this would be a temperature front or a density front here, right between 400 and 600 kilometers. And you see the velocity is strong in that region as well. And so that is a realization of thermal wind. And to get to thermal wind, you assume that the density is a combination of some constant reference density plus an anomaly, where the anomaly is a lot smaller and only becomes important when it's multiplied by the gravitational constant. And so you get, you can combine these two by taking the vertical derivative of the geostrophic balance. So you get these ddz terms, and then substituting in hydrostatic balance into that, and you're left with the vertical velocity gradient in balance with or proportional to the horizontal density gradient. So this is, and then in vector form it looks like that, and this is thermal wind. So you have the vertical velocity gradient. So here you see from this so these are direct velocity measurements. This is not calculated from a density field. This is direct measurements taken by ADCP, and these are direct temperature measurements taken by XBT. So they're two independent quantities, and you see this strong vertical gradient in velocity. So you see that the strength of the flow gets larger as you go closer to the surface, and that's associated with this horizontal density or temperature gradient. And so from that tank experiment that we that I showed stills from, you see this same dense bulge of fluid, and then on top of that, what you can't see without movement is that there are horizontal currents swirling around the top of that. So there is a bit of a vortex at the top, but not purely just of free salt water. And so thermal wind, using geostrophy and hydrostasy, you get that the horizontal density gradient is directly related to the vertical velocity gradient. And this manifests itself as vertical intensification of baroclinic fronts and jets. It's also why a lot of times, especially in oceanography, you hear jets and fronts used interchangeably because they have, because they're directly related to each other. So when you have a strong density front, you have a thermal wind jet. So just looking in the chat, Josue asks, for the experiment of salty core rotating, would the flow generate vortices as it propagates outward at the bottom, as it has to conserve PV? Not quite sure what you're asking. Feel free to unmute yourself and ask verbally.
I mean, I'm not sure. Perhaps I'm assuming something wrong, but as the salt, I mean, when you have the core, I mean, the denser core, it will tend to flow at the bottom and outwards, right? So as it's doing that, it has to conserve PV, which to me seems that it will generate vortices, but I'm not sure if that's the case. I mean, because from the pictures you show, it basically creates a cone. But I'm wondering if that cone has a 2D structure. I mean, what will be a surface or a slice of that? That's what I'm wondering. I don't know if I explain myself.
I'm not quite sure what you're asking. So if you took a slice through a cone, it would look very similar to this mean temperature picture, but it would be salty where it's cold and fresh where it's warm.
I think he means a horizontal slice.
Yeah, a horizontal slice. Yeah, that's what I meant.
He's wondering if the cone is circular This is what you're wondering?
Well, the core is circular, right? So it will, when you start, so your initial condition will be a cylinder, and it develops into a cone. But I'm curious if, as it's transitioning from a cylinder to a cone, if it generates vortices at the bottom, so at the horizontal plane at the bottom of the tank.
So the way that it adjusts between the cone and the cylinder, or sorry, the cylinder and the cone, is through smaller scale wave motions. So not necessarily vortices, but different waves carry that energy away, and you're left with this conical shape. And then depending on the scenario, if on, for example, the rotation rate and the strength of that gradient, that's how you can develop baroclinic instability. So you can get large vortices coming off that, but that isn't exactly what you're asking, I don't think. You're more interested in what's going on deeper.
Okay, that explains, I think. Cool.
Okay, and Julia says, doesn't the displacement to exterior account for change in PV? Oh, okay, never mind. Okay. Yes, so with this thermal wind balance, you see, again, this vertical intensification of the jet associated with a horizontal front. And that's convenient for observational studies because it's much easier to measure the temperature and salinity of the ocean or the temperature of the atmosphere than it is to measure the velocity. And so you can infer the velocity structure from the density field, which is a bit more straightforward to measure in the real world. Of course, for a section like this, if you only had the temperature or density field and not the direct measurements of velocity, you would only know the cross-transect velocities because of this curl. And here is a picture from the atmosphere. So the equator is here on your left, going to 90 north, and you see this warm and pressure is the vertical axis, but you can think of it as height. And you see this strong temperature gradient from the climatological mean associated with a strong westerly jet. Yes, so Kimberly asked, would it ultimately stratify after a while, even when rotating? And as Navid said, the answer is no. It actually stays in that conical shape, and that's its stable balance. It is in balance, and that is equilibrated for frictionless flows, which is what Marty and Navid are going a bit back and forth about right now in the chat. Okay, and then just another example from the Southern Ocean here. This is just a schematic, so just kind of a cartoon picture, but what you see is that these fronts or strong jets of the Southern Ocean are associated with these sort of step changes, in the density field, So because of the low Rossby number, high Reynolds number, you get this geostrophic hydrostatic balance that leads to, that can be combined into thermal wind that directly relates the horizontal density gradients with the vertical velocity gradients. And that is a stable or somewhat stable condition. And so that's sort of a summary slide for you, and that the geostrophic balance causes this rigidity or stiffness of the barotropic fluids that causes these 2D flows and Taylor columns that are not unable to have any change in velocity with the vertical and no vertical motion because of the solid boundary at the bottom. And then combined with hydrostatic, you get thermal wind, which creates this vertical intensification of baroclinic jets aligned with density fronts. And these are very important for large scale fluid dynamics on a rotating sphere. And there's a link if you want. There's tons of textbooks and different resources that you can use. Valis is a great one. Podolsky, for those that are more keen on maths, is really good. This chapter from the Weather in a Tank at MIT, Woods Hole, is really good for these balanced flows. And that, if you don't have any other questions, I will hand it over to Navid.
Good. So, do we have any questions? Perhaps before I jump to the different session. There was a nice interaction in the chat. I can see the chat filling up. So let me share my screen. Wait. Don't know if I will be able to look at the chat. So
Once you have your screen shared, across the top, it should say, have a couple of things, and then it says more. And if you click more, then you can pop the chat out.
Okay, good. Let's see. So I see. Where is the more chat? Okay, we'll put the chat here.
And we can't see your chat for the record.
Okay, good.
So we just see your slide.
Sorry, everybody. Oh, we will share lecture recordings. We will share. Everything will be shared. Yes, it will be open source. That was not a question. That was a statement. Okay, I see. Okay, let's, should we move on? What's the time? Okay, let's move on. I'm moving on. I don't hear anybody complaining, so I'm moving on. I already lost my chat window. Here it is. Okay, so what I wanted to discuss a bit with you is to give you a teaser version of what is quasi-geostrophy, which was, like it was mentioned both by Marty and by Annie a bit today. It's when flows are in almost geostrophic balance, but not quite, and they're allowed to evolve. So that's what I want to try to give you like the gist of it. So, and in order to do that, I don't want to start doing like, one can derive the quasi-geostrophic equations from, asymptotic expansions of the equations that Marty and Annie had in the beginning when you have very small Rossby number and blah, blah, blah. But I want to go in a different route that I think it's a bit more intuitive. So what my starting point will be the shallow water equations, what's called the shallow water equations. So, in a very good approximation, the atmosphere and the ocean are a very, very, very thin layer of fluids on top of the Earth. I don't know, the ocean is more or less 4 kilometer maximum depth, not maximum, mean depth, while the atmosphere is about 10 kilometers if you just consider the lower part of the atmosphere, the troposphere. So on top of on a planet that is 6,400 kilometers, it is a very thin layer of fluid. This would be a very good slide for geologists if they want to argue for funding over climate science, by the way, but hopefully they won't do that. So shallow water dynamics, or shallow fluid dynamics, because it's not necessarily only about water, it's the dynamics of this thin layer of fluids. So a simplified version of the equations that Marty and Annie had in the beginning of their slides for a thin layer of fluid. And let's start by thinking of this fluid having a constant density, a density that doesn't vary with depth, so there's no stratification, a barotropic fluid is in the GFD terminology. So why my slides don't go? Okay, so imagine this is your fluid. It has a free surface, and if we start from the vertical momentum equation, it has a bunch of terms. On the left-hand side is the inertia terms. On the right-hand side is the pressure gradient and the gravity force. And as was Marty and Annie was saying, you know, these terms on the left are really small. They are very, very small because because the vertical velocities are so small. If you put numbers there, you will see that, you know, this is like 1, 1, 1, and this is 1 million. So we might as well forget the left-hand side and just deal with the right-hand side. And this is exactly what is the hydrostatic balance. So as soon as you have that, then you can solve for pressure as a function of height. And if you impose a boundary condition at the top, say that in the top of your fluid layer, you want the pressure to be a given constant. For example, if this is the ocean, we want the pressure at the top to be the atmospheric pressure. So if we impose these boundary conditions, then we can just solve, and this is just a function of z, and it's a very simple solution that solves this equation. So here we go. We have pressure. That's one thing to put in the back. I'm just gonna show you slowly how one derives this shallow water equation. The main idea is not to, you know, perhaps you don't need to follow all the derivation, but just to see how one thinks of various terms and how eventually these all these partial derivatives and kernel identities may come alive and mean something. Because otherwise, this is a horrible subject. If you just if all these terms don't have a meaning or they're not alive, it just becomes a huge gymnastic of vector identities. So now let's go to the horizontal momentum equations, this was with rotation on a tangent plane. And now we have pressure in this, you know, in this simple system. We have solved pressure, so we can, how do you say, put the solution for the pressure here on the right-hand side. And so we get these equations for the u and v velocity. This is equations for the horizontal velocity, for the horizontal velocities. And eta is just the surface displacement, the free surface displacement. So because that's the only part, if you want to compute horizontal gradients of the pressure from the solution we found before with the hydrostatic balance, the only term that is involved that has horizontal gradients is the rho g eta term. So the sea surface height. So that's the two equations for the horizontal velocities. Now, what about the mass conservation? So if we consider a thin rectangular fluid, I don't know if you can see gray here, this gray box here. So this, in a fluid of constant density, mass conservation is the same as volume conservation. So the volume of this fluid, as this fluid is moving and this free surface is oscillating or is doing whatever it wants, the volume of this rectangle, of this rectangular, of this small rectangle here has to be conserved. So how can the volume of this fluid change? It can change because the height of this rectangle can change, can vary in time. And we can say that to a good approximation, the volume is just the height times this horizontal distance delta x. Or it can change because some fluid comes from the right into this rectangle, or comes into this rectangle from the left, or leaves out this rectangle from the right. So the flux into the fluid from the left will be proportional to the velocity at the left-hand side times the height of the rectangle at the left-hand side, and the flux out of the rectangle from the right will be the velocity at the right-hand side, and the flux of the rectangle and the height of the rectangle at the right-hand side. So to a good approximation, any change in volume should be balanced by whatever fluid comes in and then whatever fluid comes out. If you have more fluid coming in than coming out, then the volume of this rectangle should increase. The surface should go up, for example. Now, we can rewrite this. We can just multiply on the right-hand side by delta x and divide by delta x. Because when we do that, then this reminds us of the definition of the derivative, because it's just something evaluated at x plus delta x over 2 minus something evaluated at x minus delta x over 2 divided by delta x. So this is nothing but minus delta x times the partial derivative of h times u. So delta x could cancel out here, and then here we go, we can have an equation for that determines the height of the fluid at every point. We can do the same thing in the y direction, and if we gather everything, then we'll have this equation. Hopefully I haven't lost everybody. See silence in the chat. So everybody's mesmerized by all this. So here we are. So if you combine these two equations, these are the shallow water, the so-called shallow water equations. Okay, the horizontal velocities u and v evolve according to the first equation, and instead of pressure, we just have the gradients of the free surface height, and the total fluid depth at every point evolves under this second equation. And it is, of course, related to the free surface height, because the free surface height and the bottom of the position of the bottom of the fluid, if you add them together, they give you the full fluid depth. So what is interesting is that these equations admit wave solutions, and these are waves that exactly live on the surface. They can describe, they can very well describe, for example, the waves that you see in a pond when you throw a pebble in, or the waves that you see in the ocean surface when a storm comes and hits and disturbs the ocean and then goes away. So to get an idea of how these equations, what things do these equations describe, let's see an animation. Let's first forget anything about rotation and imagine we are in a pond, in a small pond, and we just start by perturbing the surface of the pond by picking it up like that. Probably this is a bit unrealistic. I should have selected to press it down a bit instead of picking it up. Pressing it down, it would be the same as just throwing a pebble in the pond. So what will happen, do you think, if as soon as we do that, what will happen? Let's see if anybody has some guess in this. No guess. Oh, wow. I lost everybody, I guess. Waves. Martin has one guess. He wants to see waves. The hope is that if waves propagating towards this direction. Okay. Somebody was. Yes. So that's what you will expect, of course. If these equations are the same as are describing what will happen in a pond, then indeed, when you throw a stone in the pond, you will see waves propagating in each direction. Horizontal velocities will increase. This is a question. Let's see. So I guess they will increase. If waves are propagating, they will increase. But then, okay, so I'm running it, giving you the answer. Indeed, we see waves propagating away. Note that these are very big distances. So this is like already 200 kilometers. And it's been only an hour or 2 hours. These waves propagate really fast. Okay, let's do it again. So if you put, now I don't see my, do you see a wave speed on the top of the speed? I guess there's a wave speed there. If only I could see that. Ah, okay. So if you go through the math, you can predict that the wave speed that these equations admit for this setup is 160 kilometers per hour. So you will expect that this wave, it will reach 100 kilometers in more or less 40 minutes. So indeed, when you let the system evolve, you see that all these waves, small scale waves, large scale waves, move symmetrically to the left and right with this speed. And after a long time, everything has moved away, and there is silence in the pond again. Now, what will happen if we also have rotation? I hate this. So the zoom obstructs me from seeing my slides. Okay. Well, I didn't want to give you the answer. I want to guess. Will the same thing happen? Let's see. This is very counterintuitive, apparently. Non-symmetrical, Isaac guesses. So you expect to see more propagation on one side than the other. So yeah. So you expect, for example, some waves will remain. Some waves will remain after a long time. So this is, what do you mean some waves will remain? So there will be some waves that will be moving much slower. So they will be still there, I guess. I guess this is, turn out waves become trapped. No, that's a good idea. That's a nice guess. Symmetrical. Felipe says symmetrical. So Isaac has guessed non-symmetrical. Felipe has guessed that it will be symmetrical. And there's, okay, I think we are ready to go. The bets have been placed on the table. I'm letting it go. Oh, no, that we saw. Let's see this one. So what do we see? We again see a lot of waves propagating away, more or less with the same speed, this 160 kilometers per second. But still there is some disturbance that is left in the middle, where the pebble we threw, or where the the initial disturbance that we put is still there. And that has led to some meridional velocity being formed and stayed there. So a disturbance that varied in x and varied in longitude has led to a meridional velocity. Perhaps this reminds you a bit of geostrophic balance, or pressure gradients that vary in the zonal direction are balanced by meridional velocities. So let's see what happened. So what happened here is that after all these waves went away, and we would have expected that our pond would come back to rest, when there was rotation, that didn't happen. The waves went away, but then we were left with something. We were left with, let's see it again here. Can I go to the end of that? Anyway, I cannot. we were left with some disturbance in the center of the domain and some meridional velocities. And if you look closely, you can see that these two disturbances are exactly in geostrophic balance. So from all these terms from the shallow water equation, in the end, after the dust settled, only the Coriolis term and the pressure gradient were non-zero in the center of the domain. And this is exactly what geostrophic balance would have predicted. So if we go back into the last snapshot of the solution and plot on top of that what the geostrophic velocity, the u and the v geostrophic velocity would have been just from geostrophic balance alone, we see that geostrophic balance, of course, predicts zero u velocity because our solutions here are one-dimensional. They don't vary in latitude, they don't vary in y, so this is exactly zero. And we see that in the middle of the domain, it is very close to zero. And if we waited long enough, also these small waves that we still see in the edges of the domain, they will have propagated away. And also you can see very nicely that on the bottom, the meridional velocity that was left, this green curve, very nicely matches the gray curve, which is exactly the solution from geostrophic balance. So what's happening here is that after all the dust settled, after all these gravity waves go away, what we're left with is geostrophically balanced motions. So the rotating shallow water dynamics can describe two types of motions. Fast traveling motions, which vary in timescales of hours, and they can be considered noise. And these slow motions that are in approximately geostrophic balance, and they vary much more slower in the atmosphere. They change in the order of days, where in the ocean it's in the order of weeks or months. And this is essentially the weather. These are these high pressure and low pressure systems that the all weather forecasts talk about, and the flows that are associated with are exactly these motions. So if we were interested about the weather of this pond, we don't really care about all these waves that propagate away and leave and propagate away with speed of 160 kilometers per hour. We're interested about this disturbance that will be left out after the waves go away. And this is exactly what quasi-geostrophic dynamics address. So quasi-geostrophic dynamics are trying to describe these slow motions, which are almost in geostrophic balance, and they vary much slower than gravity waves, ignoring the gravity waves. So imagine we want to have a way to not have to solve or not have to bother at all for all these fast gravity wave motions that propagate away. And we are only interested in these geostrophically balanced motions. That's what quasi-geostrophy does. And this was very important back in the day when they had the first weather models, because in the 70s or in the 60s, when they started doing the first weather predictions, and they were naively trying to solve the shallow water equations or the equations, the primitive equations on the sphere. As soon as they started that off, it was the whole domain was filling up with gravity waves, and because they didn't have the ability to resolve them and have small time steps and small, discretization in the spatial directions, so the models blew up. So, but when quasi-geostrophy was developed, then people were able to predict, to numerically integrate weather models. So let's discuss a bit about what are these flows in geostrophically balanced, how are they, what are their characteristics. Annie was talking about this before. So they evolve much slower than gravity waves, as we saw, and they are incompressible. So because these flows are essentially given as the gradient of the pressure, so you can see that if you take the u derivative, the x derivative of the u velocity and the y derivative of the v velocity, you'll get exactly 0. But more importantly, they follow the contours of constant pressure, if you think of a fluid with constant density, or the contours of constant P over rho F. So what does that mean? That if you plot the isocontours of pressure or pressure scale by density and Coriolis parameter, then the fluid will be always parallel to these isocontours, or the fluid will be normal to the gradient of the isocontours. And that's exactly why all weather maps show you, they talk about the pressure contours, and they show you this pressure system coming, low and high pressure systems, showing you the isocontours of pressure is an indication of how the flow will be. And so all weather forecasts are essentially using geostrophic balance without mentioning it. They should be mentioning it every time, but they don't. So as I said before, if we don't care about this noise, if we don't care about these small scale fast motions, and all we need to know is the weather, is the geostrophically balanced flow, then we can do the math and derive a simplified system that only describes the dynamics of these slow motions, and these are the quasi-geostrophic dynamics. And I won't go into details into how we do it, but somehow we do it. Okay, so remember, this is like the trailer, so we can do that in the actual school. But the gist of it is that you start from, in this case, from the rotating shallow water dynamics, which was a dynamical system that described the evolution of the u and v velocity and the free surface height. And in the end, you'll get a dynamical system for only one variable, which could be the pressure or the potential vorticity. It doesn't matter. So there is a reduction, and this system is much more simpler, and it only describes these slow motions. So you can have a much bigger time step. You can understand it much better. So perhaps I'll stop here and see if there's any questions. I've lost my chat. I've lost it completely. I have no idea what it is. I hear it is. There's no questions. Apparently, I've lost everybody. Okay. So what I wanted to discuss more further is, oh wait, there's some questions. What are the latitude boundaries in which QG is appropriate? Yes, that's a good question. Didn't really discuss that. So you see geostrophic motions means that the Coriolis parameter balances the pressure gradient. So at the tropics, the Coriolis parameter is 0. So that means that you cannot really have this classical balance between Coriolis parameter and pressure gradient there. So yes, it breaks down. So at the tropics, the quasi-geostrophic is very good approximation at the mid latitudes, for example, from 20 degrees and up. So your little simulation, can you predict? Yes, I think Maxime is asking if in this simulation, little simulation, why do you call it little? I don't know why it's little. I mean, this is very big for me. I'm joking. So in this simulation, can we predict the peak that is left after the dust settled? I think this is very related to the deformation radius, and then if so, yes, you can predict it, but I'm not really sure. I'm not sure if I'm giving this. I think the peak and the scales of the motion should be related to the deformation radius, but I'm not really sure. Is this true? Perhaps Marty, can you come?
Yeah, so I mean, this is basically called the Rossby adjustment problem. So you can actually predict the final state. And I think you're right that if the kind of scale of the initial anomaly that you put in is smaller than the Rossby radius, most of the anomaly will sort of travel out by gravity waves. If it's much larger than the Rossby radius, most of it will survive. So the fraction that's left depends on its scale.
Yes, essentially, non-zero Coriolis parameter introduces a new length scale, which is called a Rossby radius of deformation, and any flows larger than that scale will feel the rotation, while flows smaller than that scale won't feel the rotation. So flows, these initial disturbances, these small scale disturbances that I added here in the beginning, they have much smaller scale than this deformation radius, so they all propagate away happily without, us in the f equals 0 case, as they don't feel the rotation at all. So I see some other question. You said that QG leads to flows along isobars, but for evolution, don't we care about isalobars? Is there a typo there or something I don't know? Because there's a typo.
I think the isalobars relate to changes in pressure with time. Mike is basically right. So if you go back to our geostrophic balance, we threw out the whole left-hand side, which was the inertia. So that included the DDT, the actual partial derivative. So those equations actually don't tell you anything about evolution. That's why you can't just assume geostrophic balance and then go on your merry way. And that's the beauty of quasi-geostrophy, is that it allows you to assume that the flow is close to geostrophic balance, but it keeps in those time evolution terms. And so that's the part that depends on isolobaric flow and all that.
So I guess, yeah, Marty is right. And, what I did is to hide this under this purple box. Yeah, there is some, yeah, I mean, in the end, quasi-geostrophic dynamics gives you, it's a dynamical system. So it gives you something, so how the flow evolves. So I guess there will be a DDT, there will be an inertia term. But without all these fast motions, hopefully that we answer Mike's question. In the tank, so there's a new question. Let's see. In the tank experiment yesterday. I think so. Ewan asks that he noticed in the tank experiment that the initially noisy turbulence was settling down into some stable wave patterns or vortices. And he was asking if this is sort of quasi-geostrophic tending towards geostrophy. And yes, I think the answer is that essentially the dynamics that govern these large-scale vortices in the tank are quasi-geostrophic dynamics. So those are where, so after the dust settle, even in the rotary tank, after the geostrophic adjustment. So, somebody put their hand in and wiggled the water. So there were some gravity waves all around the place. They dissipated, they went away. And what you were left in was these large scale vortices, which were essentially quasi-balanced flows. Okay. Perhaps we should proceed. So what I wanted to discuss a bit more is this statement that Marty made yesterday. Both Marty and Annie touched on that rotating fluids behave as two-dimensional. They become two-dimensional. So, and what I want to touch is how does quasi-geostrophic dynamics relates to this, to 2D turbulence. And as you know, the answer is downstairs. It's a long time. Okay, I see Annie's continuing the chat. I'll close the chat. The chat, it obstructs me a bit. Okay, I'll put it on the side. So the answer is in this parenthesis that a compressible two-dimensional flow is quasi-geostrophy without rotation. And let's see what. So let's discuss a bit of what is you know, how the equations for a compressible two-dimensional flow look like. So if you start, you know, with equations of motions for a two-dimensional flow that it's only in x and y and only has two flow components, and we've neglected you know, viscosity here. We have the pressure gradient on the right-hand side and the inertia terms on the left-hand side, and the flow is incompressible, so the divergence of the flow is 0. We can do two things. First of all, because the flow is incompressible, we can write the flow in terms of a string function. So this is a usual trick people do. So as if you write u and v as partial derivatives of some function psi in this way, then the equation, the divergence equation, is identically satisfied. So we can forget all about it. And the other thing that people do is that, you know, they don't want to be dealing with this pressure term on the right-hand side. And the way you can kill this pressure term is by taking the curl, because the curl of a gradient is 0. So instead of looking at the evolution of the flow, we consider the evolution of the vorticity of the flow. So, and because this is a two-dimensional flow, it has only vorticity in the normal component, so only in the z, in the direction perpendicular to the fluid of motion. So, and using these identities here and some other vector identities, you can see that this vorticity component is just the Laplacian of this function psi. So then, if you take these equations of motion and take the curl, you can derive this seemingly simpler equation, which is just an equation, you know, the pressure gradient has gone out of the window, and it's only an equation that, that involves psi, because the flow here is given in terms of psi. So from a system with 3 variables, u, v, and pressure, we get a system with only 1 variable, psi, to solve for. Now, if you derive quasi-geostrophic dynamics without rotation, you will end up with these equations on the right here. And you can see that they are exactly identical with the incompressible two-dimensional flow without rotation. So a compressible two-dimensional flow without rotation is completely identical with the quasi-geostrophic dynamics without rotation. So instead of psi here, instead of this string function psi, we have pressure over scale by density and Coriolis parameter. So, so also note that these equations, they are very similar to the passive tracer equation, which describes how a tracer, how a die evolves in a two-dimensional flow. So in this case, theta doesn't affect the flow, while in the case of a two-dimensional flow, we don't have the temperature or the concentration of the die. We have the vorticity. The vorticity does affect the flow. This is an active tracer equation, but the similarity is of note. So how does a two-dimensional flow looks like? So I will show you here a simulation of how the vorticity evolves if I start from a vorticity configuration, which is like that. So you know, random blue and random positive and negative vorticity patches all over the place. When you see red, it means that the fluid has a tendency to, has positive vorticity, which means tendency to rotate counterclockwise, while blue means tendency to rotate clockwise. And if we let this system go, we see what Marty was talking about yesterday. We see this propensity of the fluid to make, to give energy to the larger scale. So all these vortices tend to merge together into bigger vortices. Small vortices merge with small vortices and create larger vortices. So energy goes into that larger scales. And if we let the simulation run long enough, you will end up with one big red vortex and one big blue vortex. Don't know if you can, hopefully you can see this video. This is mesmerizing, I really like this video. Now, what does this has to do with rotating fluids? So if you take a snapshot of that video, you will see that 2D turbulence has this property that you know, that positive and negative vorticity tend not to mix well enough. So they create these striations of vorticity. And if you think of the vorticity, of course, this is not a very, it's not a perfect analogy, but because of this analogy of the two-dimensional vorticity equation with the passive tracer equation, the vorticity can be thought a bit like a die on the top of a fluid. Then you can see how the die in the rotating tank experiment we were seeing yesterday shows structure and that resembles the animation of 2D turbulence, of the 2D turbulence. So this is like a demonstration of how 2D turbulence without rotation resembles three-dimensional fluid in a rotating tank. So in other words, how rotation in the experiment makes the fluid behave more as if it is two-dimensional. And now, yeah.
Can you clarify what you mean by QG without rotation?
Yes. So, okay, what I mean with,
you did have F in there.
Yes, okay. What I meant without rotation, QG without rotation, I should have been more clear. I meant that the Coriolis parameter was just a constant and did not vary with latitude. So essentially it's without beta. That's what I meant. Then these equations are, so this is just a constant F, just F naught. I should have put an F naught there. Hopefully that clears it up. Yeah.
Yeah, so we're on a rotating plane, not a rotating sphere.
Yeah, we are in an F plane, not in a, not on a sphere. So if you're on an F plane, quasi-geostrophy is exactly mathematically identical with two-dimensional turbulence.
Thank you.
Now, if you have rotation, so if you have a Coriolis parameter that varies with latitude, if you are on a sphere, the quasi-geostrophic dynamics become this. So now what's the equivalent of the passive tracer quantity is not just the vorticity, but it's the vorticity plus the Coriolis parameter. And this is what people refer to as potential vorticity. So it's the potential vorticity of the fluid that acts as if it was a tracer, as if it was a die. And this equation at the top essentially says that this quantity, the potential vorticity, is what is materially conserved. So every fluid particle of if you follow every fluid particle, every particle with the flow, its potential vorticity has to remain the same. And this, of course, ignores any depth variation. If you add depth variation, then this potential vorticity quantity has also depth in it. It has to be scaled by the total depth of the fluid. But the idea is that you know, the more complexity you add in the system, you can always find a quantity which you can call PV, potential vorticity, that is materially conserved in an inviscid fluid, and such quantities are really helpful for understanding and how the dynamics of the flow will you know, behave. So if we now allow some variation of the Coriolis parameter with latitude, we can see how that affects the structure of the flow. So on the left, we have what we were seeing before. So non-rotating, essentially, you know, F plane, the Coriolis parameter is constant. I took it 0 here, but it's constant everywhere. And here, Coriolis parameter that varies with latitude. I introduced a new constant here, which I call beta. And so my Coriolis parameter varies linearly with latitude. And we see that the flow on the right behaves very differently from the flow on the left. We see some vortices merging, but what we clearly see is that the flow becomes very anisotropic and very zonally, the flow is very zonally and elongated, very different in the zonal direction than in the meridional direction. And you can see that jets have formed, 2 or 3 jets have formed, and you can also see that this quantity that we call potential vorticity has formed these sharp fronts, that it's very mixed here, and then you can see a jump, and then very well mixed here. I don't know if it's very clear by a zoom, but you can see that this, you know, the PV structure on the right it seems as if it has formed 3 or 4 zones of nice mixed PV. So this is another, so this is to demonstrate how rotation and how variation of the rotation with latitude, so you know, living on a sphere can have a tremendous effect on the structure of the fluid flow. Perhaps that's it. Okay, yes. So, and just to remind you that all this discussion this past 2 days was just a preview, and the real thing will be hopefully next year. So with this, I'll stop and go see the chat if I can find it. Here it is. Okay, how do we go out? What happened? I've lost everybody, I guess. There's silence. It's very weird with this silence.
I think I stopped your share.
Oh, okay.
And now we can see everybody who's still hiding for us for questions.
So there's a few questions in the chat.
Ah, okay. Oh, but how close to the equator does the F-plane approximation become wrong? Why zones? Why PV zones? These are very good questions. Okay.
So the farther from to comment on Maxim's question,
yeah.
The farther from the equation, or farther from the equator, the F plane, is still a good approximation over hundreds of kilometers. Even at 60 south, 60 north, it's still a good approximation. But when you start spanning thousands of kilometers, that's when it becomes questionable. And then geostrophy itself, where F goes to 0 at the equator, which is a different question, but maybe important information. That's plus or minus 5 to 10 degrees of latitude is where geostrophy is no longer, or QG is no longer really the major balance. So it's only really kind of confined there to the equator that QG and geostrophy are not, where F is no longer important. And then, yeah, the F plane, it depends on how large your meridional scale is. And so again, at 60 south, 60 north, even a couple hundred kilometers is still, that's a good approximation. F only changes. You can do it at home if you want. You can calculate how much F changes over a couple degrees of latitude there, and it's very, very, very small.
So Corey has a question about, we want to clarify, when you were talking about potential vorticity here, is it the same as absolute vorticity? Yes. So indeed, in all the examples I've gave the potential vorticity is the same as absolute vorticity. So the vorticity of the fluid as you would see it from an inertial frame of reference outside that doesn't rotate with the Earth. So that's why we add the Coriolis parameter, which is essentially the vorticity associated with the solid body rotation. And that's why if we have a fluid of varying depth, we have to scale by the height of the fluid because the shorter the fluid, the higher the vorticity is. Yes. Why?
Well,
No,
yeah,
go.
I was going to sort of make a comment relating to Mike and Devang's question. So they're asking basically, why do we get jets and why are they and why do you get these zones of PV? And so one way of kind of thinking about that is the PV, the potential vorticity in the kind of systems that Navid has talked about is conserved, so it kind of just flows around with the flow. And so if you think about how would a turbulence affect the distribution of a conserved tracer, you might think, well, it'll mix it. So if there's an initial gradient in its conserved tracer, it'll try and mix out that gradient. And so it might, if you have a F increasing with latitude as it does on rotating planets, then the turbulence will try and kind of reduce that gradient. But what happens, because PV is not a passive tracer, because it affects the flow, when you have certain configurations of the PV, that will actually enhance or reduce the mixing. And so what happens is when you get a very strong PV gradient, the efficiency with which turbulence can mix across that PV gradient is reduced. And so this sets up a feedback where you can have regions where the PV gets really mixed, so you just get one sort of value of PV in that region, separated by these barriers, these mixing barriers, which are very strong gradients of PV, which correspond to jets, basically. And so because of this feedback process, you can actually set up what's called a PV staircase. So you get one value of PV for a certain distance, and then a big jump, so a PV front, and then another value of PV for the northwards. I don't know if that is the kind of picture you think about, Navid.
Yeah, I mean that's qualitatively it is. That's right. I don't know if also the question was referring to why zones in X and not in Y. Perhaps, I don't know. So I mean,
and it forms zonal jets because the Coriolis parameter varies with latitude but not longitude, and so that beta effect causes these zonal bands.
Yeah, and also that variation gives rise to Rossby waves that travel in the zonal direction most predominantly. All these things are intertwined. So, but yeah, the essence is what Marty said before. Hopefully this was a promotion for the summer school and not for the winter school, and not a discouragement.
Okay, it looks like our questions have quietened down.
They have stratified. The chat has stratified.
So yeah, as Navid said, this is a trailer. We will run this a whole week. It's going to be awesome. As soon as we open up again, we will run a full atmosphere, ocean dynamics, winter, spring, summer, autumn school when we can fit it in. So for now, let's thank our 3 speakers for the last 2 days, Navid, Annie and Marty. We've got lots of little claps wheels coming up. As I mentioned, we'll put material up on the website for these 2 days. Give us a little bit of time to sort that out, a week or 2. I'll put an announcement in the weekly update once they're up. Tomorrow we're going to move on to a little bit of researcher development, and James Goldie is going to talk about data visualization. And he suggested that if you have a plot that you've been working on that you're struggling with, bring it along. If not, we're all going to critically assess some of James's plots from earlier in his research career, so he's been quite brave. Yeah, so bring those along, same time, same place tomorrow at 1 o'clock. So yeah, thank you everybody.